Yes, thanks very much, Ian. It's great to see everybody here. And as Ian said, I think New Zealand, we're really pleased to have been involved in GEM right from the beginning, and will continue to do so. But my little task here now is a real pleasure to introduce Marco Pagani as the speaker to address the hazard aspects of the GEM models. I've known Marco for quite some time, being a geologist also. It's been a really long journey, I think, for the hazard, getting the hazard connected up and across the globe. I would say that GEM is extremely fortunate to have had somebody of the calibre of Marco that's hung in there for this long journey. I think I knew Marco first, maybe it was the European Share Project or something even before GEM, but we're extremely fortunate to have had Marco sticking at this. It's a tremendously big task to bring all of the hazard components together around the world. There's been some robust conversations over the years, but I would say that Marco's just a great guy that gets on with things, huge stickability, and with great pleasure I'd ask Marco to come to tell us what he's been up to.
So good morning, and thank you very much, Kelvin, for your very kind words. I think that GEM was actually very lucky to have a very good team of people working in the hazard team. It's not just me. Actually, my contribution is very minimal compared to the one of many of the people that you see listed there, and probably of many other people that I cannot list there, but that contributed a lot to the construction of what we are presenting today. And as it was already pointed out previously by John and by Mauro, GEM started in 2009, and within the hazard team, throughout the years, we did a lot of tests and experiments in order to exercise our capability to develop hazard models at regional and national level. We started actually quite early, and in 2010, at the end of the GEM 1 project, which was the pilot project that gave a start to the GEM initiative, we had the first global hazard map, which was a kind of patchwork combining some regional models with a global smoothed seismicity model. Later on, in 2012, we took part to the GAR initiative, and we developed a global hazard model based on a smoothed seismicity approach that was used as part of the GAR initiative. In 2013, at the end of the first implementation phase, we released a first compilation of models for the OpenQuake engine that, as you can see, had a partial coverage at global scale with vast areas that were unfortunately not yet covered at the time. And because of the need to have a clear definition of goals and a clear definition of deadlines, in 2015, the GEM Governing Board created a specific task force that defined the approach and the methodology that should be used in order to get at 2018, at the end of 2018, today, with the construction and with the release of a global compilation of models and a global hazard map. So what I'm presenting today is mostly work that concentrated over the last 3 years. But clearly the last 3 years are the result of the experience and all the work that we've been doing also in the previous years. So my presentation is subdivided in 4 main topics. And I'm starting with the definition of what we consider our framework for the modeling of hazard at the global scale. Then I will give you a description of the mosaic, and in particular of the criteria that we used to select the models that are part of this mosaic, and the components, so the various models that we've been using for the calculation of the global hazard map. Then I will show you the map, and I will give you some information about this map. And at the end, I will explain what we think we will be doing starting tomorrow. Maybe tomorrow we will rest a little bit. So let's start with the definition of the framework, because that's really at the core of what we are releasing today. The map is in reality just a product that is created by this framework. And in order to define the framework, I think it's important to start with a brief discussion about the approach that is behind the framework that we created. So for the construction of a global hazard model, there are fundamentally two different approaches. And this is part of the discussion that we had with the task force in 2015. There are two options, basically, two recipes. One that is top-down. So you take a core group of scientists and you ask them to work quite closely together for a couple of years and to come up with a model. The second option instead is a bottom-up approach. So it's an approach that is using as much as possible resources, models, and expertise that is available at the local level. And when we decided the methodology to be used, the approach to be used, clearly our option went in line. So we went with the second option because clearly that's more in line with the mandate and with the fundamental principles that are at the basis of GEM. And we thought that was also a good option because that was more in line with previous experiences that demonstrated to be actually solid and capable to generate results that lasted with years, like the GSHAP project. So the GSHAP project was definitely a quite successful project because it produced outstanding technical achievements, because it involved a very large community of scientists, and because it represented a milestone for seismic hazard modeling at global level, but also at regional and national levels in many parts of the world. If we want to find, let's say, tiny defects or negative aspects of GSHAP, they are, in our opinion, the fact that it remained almost the same model for almost 20 years, and now, unfortunately, is no longer completely reproducible because some of the models are no longer accessible. More in general, if still discussing about the bottom-up approach, clearly the bottom-up approach has pros and cons, and this is important to take into account because when you define the framework, you want to maximize the positive aspects and minimize the negative aspects. So the negative aspects are clearly that the models that are part of the mosaic are heterogeneous because they've been developed using different methodologies. But on the other hand, if you follow an approach that is trying to collect the models developed by the community, this is certainly helping in summarizing and getting the most recent science available in various parts of the world. And it's also a way to engage and involve the community as a whole and try to work together for improving and creating models that are more advanced and more homogeneous with time. Of course, it's a process that is taking time. So what we come up with is this framework. And it's a framework that is not just aimed at building a map, but it's a framework that is including the data sets, like the one that were created by the global components supported by GEM during the first implementation phase, and the data sets, for example, that we are building when we are working at the regional level. It's a framework that is including methodologies for developing the models that we are releasing openly, that can be used by other scientists, that can be changed or criticized, but it's an open and transparent way to develop models in this way and to make progress together. We have an engine that is now extensively used, and it's a way to homogenize the models, at least in the way that the models are represented. And part of that is clearly the mosaic, which is a collection of models that we use for generating the map. If we focus on the mosaic, which are the criteria that we've been using in order to compile the collection of models that we used so far. And in order to select the models, in every area we applied these criteria, starting from the most preferable one and going to the one that was a kind of last option. So the models that we prefer to use when we look at one region are the models that are developed by either national agencies or by large international projects that are involving a large community of people. If a model of this type is not available for a region, the next step that we took was to look into the literature and try to find a model that was recognized from a scientific point of view and developed in most of the cases by a smaller number of scientists. This is, for example, the case of the model that we are currently using for India. If for a certain region there's not in the literature a model that is credible and robust, the last option that we went through, which is something that we decided finally to adopt in 2015, is to develop a model internally. And as you will see, there are unfortunately some reasons where we've been kind of forced to develop models internally. But clearly, we are not losing the hope that in the future, in these areas, there will be the possibility to develop new initiatives involving the local community. So one important point is that all the models that are part of the mosaic are represented with the same file format. So they are described in a standardized way, which is the way that we use to describe the input models for the OpenQuake engine. So what does that mean? It means that when we decided to use a model that was originally developed using a different software, either at the Secretariat or through collaborating organizations, such as in the case, for example, of GNS Science, as it is mentioned in this slide, we develop code to translate the original model into the OpenQuake engine. And when we do that, of course, we invest a lot of time in order to make sure that the values calculated with our implementation of that model are as close as possible to the original results. It's not an easy task. I can guarantee that. So these are the selection criteria. Which are the components of the mosaic that we are using? So first of all, there are essentially four typologies of models that are part of the mosaic. One typology of model is including regional and national models, developed, again, as I said, by international projects or well-recognized national organizations. And those are represented in pink in this map. There are also some models developed within international projects that were coordinated by GEM, and I'm referring in particular to the ones in South America, Central America and the Caribbean, and Sub-Saharan Africa. Then we have one model that was mostly taken from the literature, and we have a few models, the ones that are represented with this hash pattern, that were created internally by GEM. So if we focus now on the different regions, I'm going to provide you a very brief description of the various models. So in the Americas, we have, in the northern part, as you can see, models that were mostly developed by two well-recognized national organizations. So we have been using models developed by the USGS for Alaska, for the conterminous part of the OUS, and for Hawaii. Note that in the United States, we are splitting California from the rest of the United States because for California, we implemented a user-free model, which is probably one of the most complex models at subnational scale. In Latin America, instead, most of the models were developed within GEM through few international projects or in a completely internal way. Mexico was completely developed internally, whereas for Central America and the Caribbean and South America, we had projects in one case called SARA and ended in 2016, and a more recent project in Central America and the Caribbean that ended in 2018, both supported by USAID. In Europe and Africa, the situation is similar to the one that we saw for the Americas. So in the northern part, we have a model that was created within a project funded by the European Union. Sorry, the text is a bit screwed up. And it's a project that was coordinated by the Swiss Seismological Service, IDTH. It's the first regional program of GEM. And it was actually a project that was used a lot, not just to create a NASAR map, but in order to test and develop components of the OpenQuake engine. In Africa, instead, we have two models that were developed internally, Northern Africa and Western Africa. One model that was created in collaboration with Africa Array, which is an initiative quite active in Sub-Saharan Africa in particular. And for South Africa, we have a very recent model that was developed by the Council of Geoscience. It's the National Hazard Model for South Africa. It's not yet published, by the way. Asia is definitely the most complex area of the mosaic, as you can see from this slide. And so in Asia, starting from the north, we have two models that were again developed internally, because in Russia, unfortunately, we didn't manage to establish a collaboration. So Northwestern Asia and Northeastern Eurasia are two models that we created internally. Then we have the model for the Middle East that was created within the EMME project, a project led jointly by ETH, the Swiss Seismological Service, and Query. The model for Central Asia, which was coordinated by the Geofford Centrum in Potsdam, and it was created through the EMCA initiative. Then we have a model for the Saudi Peninsula that was created by the Saudi Geological Survey that they kindly share with us. The model for India that I mentioned earlier on, taken from literature, but we have a quite close collaboration with the authors, and in particular with Thinbajan. The latest National Seismic Hazard Model for China that we implemented in the OpenQuake engine through a collaboration, again, with the Swiss Seismological Service and with the China Earthquake Administration. The model for Southeast Asia, which is a project jointly created by the Maidol University in Thailand and the Earth Observatory in Singapore. The latest National Seismic Hazard Model for Indonesia that was released in 2017. A model for the Philippines that was initially created by PHIVOLCS and improved through a collaboration between PHIVOLCS and GEM. The latest model for Taiwan created by the TEM project. The 2014 model for Japan created by HERP and implemented in the OpenQuake engine through a collaboration between GEM and NID. And then we have a model for Korea, which is a sort of hybrid model, which is using sources from the China model and the Japan model. Probably the weakest model we have at present in the mosaic. Moving to the last part of the world, so in Oceania we have the National Hazard Model for Australia, which was released 2 months ago. It was a model developed for the OpenQuake engine, so for us it was super fast, integrating that model into our mosaic. We have a model for Papua New Guinea that was created through a collaboration between Geoscience Australia and the Port Moresby Geophysical Observatory. A model for the Pacific Islands that was created internally at GEM, and an upgraded model for New Zealand. So they took the 2010 model and they started to introduce changes that probably will be also used for the next generation of the National Seismic Hazard Model for New Zealand. And that's also a model that was completely implemented by GNS Science for the OpenQuake engine. I think that one important aspect that it's important to emphasize is that the vast majority of the models that are part of the mosaic are incorporating epistemic uncertainty. And this is probably one distinctive difference if you compare the mosaic that we have and the models that were in the G-Sharp model. So in this slide, I'm showing with this hashed pattern the models that are including epistemic uncertainties for the seismic source characterization as well as for the ground motion characterization. In purple, you see the models that are only considering epistemic uncertainty for the ground motion characterization, and in green, the few ones that are not yet considering epistemic uncertainty. So this is very important, not because in this way we have the full capability of exploring the entire range of uncertainty admitted by a model, but because in this way the mean hazard that we are calculating is far more robust than the one that we get if we don't consider epistemic uncertainties. Next part is the hazard map. And this is the hazard map that results from the combination of the maps that we calculate considering the 30 models that I just explained to you. The map is representing PGA with 10% probability of exceedance in 50 years and is referring to reference fault conditions that are in the range between 760 and 800 meters per second. As you can see, the hazard is, changes smoothly between the various models, and in order to guarantee that, what we did is to apply an homogenization procedure that is concentrated on narrow bands of a width of about 120 kilometers between the different models. So some information about the map. So as I said, we started from 30 hazard input models. From 30 hazard input models, if you take into account the epistemic uncertainties in the seismic source characterization, you get to more than 100 seismic source input models. And if you use that models to generate, and you count the number of sources that are included in those models, you come up with about 3.5 million of sources overall. And if you generate all the ruptures using all that sources, you get about 1.8 billion of ruptures. So that's what we use to calculate the map that you see there. And in terms of ground motion characterization, the model is using about 90 ground motion prediction equations that, of course, are all implemented in the OpenQuake engine. Now I'm showing you some comparisons, some analysis that are, I would call them still preliminary because this is work that we did over the last week. Okay? And I'm starting with some comparisons between the hazard results in the GEM map and the G-Sharp map. And in order to show this comparison, what I'm doing is the following. I'm fixing a value of hazard, in this case 0.1 G. And I'm looking at the GEM and G-Sharp model. If both the models are exceeding that value of ground motion, I'm putting a green dot. If only the G-Sharp model is exceeding that value of ground motion, I'm putting a blue point. And if instead only the GEM model is exceeding that value of ground motion, I'm putting a red dot. So what you can see from this plot is that considering this threshold, the pattern of hazard between the GEM model and the G-Sharp model is actually reasonably good. So there's a good match. There are, of course, some differences. For example, you can see that Australia is in the G-Sharp model showing higher values of hazard compared to the GEM model. That in India, for example, the GEM model is giving higher results than the G-Sharp model, but overall, the pattern is consistent. If we increase a little bit this threshold, so we look at the areas where the hazard is slightly higher, so now you can start to see some differences. And in particular, you can see two fundamental patterns in the two hazard models. So the GEM model is concentrating the highest values of hazard in California and along the subductions. So you can see Western western coast of South America, Papua New Guinea, Indonesia, Japan. Whereas in the case of the G-SHAP model, there are areas of hazard concentrated along the Alpine Himalayan chain and in the Tian Shan area. And this pattern is even more emphasized if we increase even more the threshold at 0.5. Okay? You can see that G-SHAP is giving high values here, GEM is giving higher values along the Himalayan thrusts, in PNG, again, Philippines, and South America, Central America. Second type of analysis. So now I'm showing you every line that you see there with a color and a code on top of it is a magnitude frequency distribution, and it's a cumulative one. So if you take a value of magnitude and you take this value, this is telling you the number of earthquakes larger than that value of magnitude occurring every year in that model. If we sum up all those magnitude frequency distributions, okay, and we calculate this red dashed line that you see here, that's the global magnitude frequency distribution that we get from our mosaic. Of course, when we have models with epistemic uncertainties, I'm choosing one model. And note that in this exercise, I am not including at this point Japan and USURF model because it was too complex and it was not compatible with the time that I had. But nonetheless, okay, I think that the test is still quite interesting. So I'm finishing. So the last curve that I need to explain to you is the one with these blue dots. That is the experimental magnitude frequency distribution that you get if you take the earthquakes in the ICGEM global catalog starting from 1960. And the match between the two is kind of astonishing. Okay? It's true that most probably in our case we are slightly overestimating the hazard or the occurrence of earthquakes because the ICGEM catalog is not declustered. I did not decluster it. But nonetheless, I think that the match between observation and what is provided by the model is quite good, and even for me was quite surprising. I'm moving to the last part of my talk, and the last part of my talk is what's next. And what is next is clearly starting from what I explained in the initial part of my talk. So we have a framework, and the framework is definitely the tool, the instrument that we will use in order to maintain and improve the mosaic and the collection of models that we have. So the framework includes data sets, like, for example, the Global Active Fault database that we completed this year, and it's available online. We have not just data sets, but methods. And this is, for example, a kind of standardized method that we developed for building subduction sources in the mosaic. So the models developed by GEM that are in part of the mosaic, so if they consider subduction sources, those subduction sources were created following this workflow. And most of all, we have an engine, and we have a calculation engine that is now extensively used around the world. In this map, I'm showing you, for example, in yellow, the models for which the models that were created directly for the OpenQuake engine. And in purple, you see the models that were created for a different software and converted into the OpenQuake engine. And in a perspective, part of this map will change because now, for example, we are collaborating closely with Natural Resources Canada, and the next generation of the national hazard maps in Canada will be computed with the OpenQuake engine. And similarly, for example, in New Zealand. We are also collaborating with the China Earthquake Administration, and maybe they will also decide in the future to use the OpenQuake engine. So, getting to the conclusion, what we will do starting from Monday next week. We will start, once there will be an approval by the government, to define the plan for releasing the models, and this will go through the entire 2019. So releasing a model means that we put on our website the input models for the OpenQuake engine. Of course, when the models were developed by third parties, we need to discuss and agree with the original authors. We'll put the results. We'll put a description that is outlining the fundamental characteristics of every model, and this is the main page of the website where we are starting to compile all those descriptions. And we will continue in collaborating with various organizations for the construction of models, for the calculation of models, for the use of the OpenQuake engine in national seismic hazard mapping. For example, now we are working with Italy because Italy is finishing the next seismic hazard maps, but we have plenty of other collaborations. We'll start planning the upgrade of models that most probably will be made available soon, like the model for the Korean Peninsula, because that's very needed, the model for Japan, because now we are using the 2013 version, the new model for US that will be released in 2020, the Canada model, also released in 2020, the new SERA model for Europe. And of course, since we have a framework, once those models will be rendered available, we will have the capability to incorporate those models into our framework and to update the map. So to have a new map that is relying on the most updated and most advanced models available and openly accessible. So I'm finishing with some of the acknowledgements. Of course, there's a long list, and I don't think that I can be comprehensive as I should be. But certainly, we would like to thank the public and the private organizations that supported GEM, because without them, it would have been impossible to get here. The staff at GEM, because what I'm presenting is the result of a joint effort. It's not just my effort or the hazard team effort. The organizations and the scientists that contributed to the construction of the mosaic, because most of the mosaic is actually relying on models that were developed by external or collaborating organizations, okay? And this is something that is important to praise. And the organizations, the initiatives that collaborated with the hazard team, I'm thinking, for example, to OGS Trieste, but there are plenty of organizations that have been working with us throughout the years that we definitely would like to thank you. I also have 3 personal acknowledgements to do. Well, the first one to my bosses, starting from Domenico and Stefan, going to Rui, Anselm, and John, because they've been really patient with me, and I know that in some cases you really need a lot of patience with me. My staff, because they've been also definitely very patient with me. And my family, because throughout all these years, they've been really helping me, also in periods where I've been certainly not dedicating enough time to them because I was working on other things. Okay. Thank you very much.